In distance vector routing, each router maintains a table that lists the shortest known distance to every other node in the network and the next hop to reach it. Each router periodically exchanges its table, or distance vector, with its neighbors. When a router receives updates, it adds the cost to the neighbor and checks if the new path is shorter. If it is, the table is updated. This process continues until all routers converge on the shortest paths. This algorithm assumes fixed link costs and resembles the Bellman-Ford algorithm, where each node relies only on local knowledge from neighbors. It's simple and distributed, but slower to converge compared to link state approaches. This example illustrates the dynamics of distance vector routing using node A as an example. At time 0, A only knows the cost to its immediate neighbors, B and F. After one period t, it receives the distance vectors from B and F. It adds the cost to reach B or F and uses their advertised distances to update its own table, which is now available at time 2t. This update process continues periodically, with A incorporating the latest vectors from its neighbors. As shown in the timeline on the right, A's routing table becomes progressively more complete with each round, ultimately converging to reflect the shortest paths to all nodes in the network. This iterative method exemplifies the distributed nature of the distance vector algorithm. This example builds on the previous distance vector scenario, but introduces a topology change over time. Initially, node A computes its routing table by receiving distance vectors from B and F. But now, two events happen. At time t equal to capital T plus epsilon, the link between nodes D and E breaks, which effectively removes the direct route from E to D. At time t equal to 2t plus epsilon, the cost of the link between E and F increases from 2 to 3. These changes propagate through the network using the distance vectors. Each node updates its routing table based on the new information it receives from its neighbors. Looking at the sequence, at tt equal to 2t, A uses vectors from B and F and still sees the old cost to D via F and E. By t equal to 3t, F realizes that reaching D now requires a longer or invalid path due to the failure. This incorrect info may temporarily result in routing loops or incorrect paths, which is a known weakness of distance vector protocols. At t equal to 4t and t equal to 5t, node A updates its table again as corrected information propagates, eventually stabilizing to reflect the new network state. Let's look at this second example of the distance vector algorithm, where we observe how node A gradually builds its routing table across multiple iterations. Initially, at step h equal to 1, A only knows about its direct neighbors, B, E, and F. It learns their distances and adds them to the routing table with the corresponding costs, 1 to B, 2 to F, and 4 to E. At h equal to 2, A receives the distance vectors from those neighbors. For instance, B tells A about its own connection to C and D. As a result, A updates its table and learns it can reach C through B with a total cost of 3. Similarly, F informs A about D, so A adds a route to D via F at cost 4. By step h equal to 3, additional updates help A learn about new nodes like G and confirm or improve existing paths. The process continues at h equal to 4, where A now has complete knowledge of all reachable nodes and chooses the paths with the lowest cumulative cost. Let's see what happens in case of a topology change, such as the addition of a new node. Initially, nodes A, B, and C are connected, and a new node D becomes reachable when a link is added between C and D. In step 1, node C updates its table and immediately knows it can reach D with a cost of 1. In step 2, C informs B about this new route, and B adds an entry for D with a cost of 2 via C. By step 3, B informs A, which then adds D with a cost of 3 through B. So the update propagates hop by hop, with each node simply forwarding the best information it receives from its neighbors. This example shows a classic problem in distance vector routing called the count to infinity issue. We use the same network setup, but now node D becomes unreachable, for example due to a failure of the link between C and D. Initially, C detects that D is unreachable and sets its cost to infinity, but A and B still believe they can reach D through each other. At step 2, C tells B that D is unreachable, But B still thinks A can reach D, so B sets its cost to 4. Then A, seeing B's new cost, updates its cost to 5, and so on. Each time, the cost increases by 1 as the misinformation propagates. Eventually, the cost grows toward infinity, a slow convergence and waste of resources. This highlights a weakness of distance vector. Bad news travels slowly. To fix the count to infinity problem, distance vector routing uses a technique called split horizon. The idea is simple. If a router learns about a route from a neighbor, it doesn't advertise that same route back to that neighbor. Otherwise, we get the looping behavior seen in the previous example. There's also a stronger variant called split horizon with poisoned reverse, where the router explicitly tells its neighbor the route has a cost of infinity. In this example, when node D becomes unreachable, C sets its cost to infinite and tells B. Because of split horizon, B does not send back to C a fake route to D via A, so C doesn't get misled. At the next step, A also realizes D is unreachable and sets its cost to infinite. The issue is resolved in just a couple of steps, with no looping or long convergence. This technique improves stability and prevents routing loops caused by outdated or misleading information. ARPANET, the early form of today's Internet, initially used the distance vector algorithm until 1979. It updated routes every 125 milliseconds and was based on queue length as a cost metric. But this design had a major drawback. It was too slow to adapt when network conditions changed rapidly. That led to the adoption of the link state algorithm in 1979. In this approach, each router estimates delay to its neighbors and floods that information throughout the network. This allows every router to compute the best paths independently using global information. It's more reactive and converges faster. With link state, update intervals were increased to around 10 seconds, significantly reducing overhead and improving stability in dynamic environments.